Awesome. So thank you so much for this opportunity. Let me start by saying that some of the results that I'm going to present today are not in the paper that we currently have up on our websites. This is because this paper is being revised, and we hope to have the new results and we hope to have the new revision uploaded soon. Okay, so with that being said, let me start by an introduction. What we do in this paper is we ask, how does economies of density shape the spatial distribution of supply in spatial markets? And we focus on the context of ride sharing, asking three questions basically. First, we ask, what does theory say about driver behavior, efficiency, platform optimal response as they relate to density and spatial distribution of supply? Then we ask, okay, how do we empirically test these implications of the theory and the impact of density on how supply is spatially distributed? And finally, we think about the implications of this work for policy and business strategy and ask what those implications are. Okay, so what I'm going to do next is I'm going to give you our quick answers to these three questions. And then for the remaining time, I'm going to try to get into as much of the details as possible. So on the theory side, what we do is we build an equilibrium model of driver decision-making on where to operate, where to locate within a spatial market. And what we find out is that in the equilibrium, drivers are going to have a distribution that is skewed towards the regions with higher density of demand. To sort of illustrate this, imagine region I has twice as much demand per square mile as region J. We showed that in the equilibrium, say 3 times as much supply per square mile is going to go to region I compared to region J, which means potential demand is going to be more likely to go unfulfilled in less dense regions. Then we ask, okay, is the platform on board with this or not? And then we sort of think about this issue from the perspective of the platform. And it turns out that the platform itself does desire some level of skew in terms of supply spatially from demand, but not as much as it arises in the equilibrium. Therefore, we show that the platform should encourage a more even distribution of drivers through using wages and prices as levers. And finally, we show that all of these problems above, the skew of drivers, the skew of supply distribution from demand, and the reaction of the platform, all are more pronounced for smaller platforms compared to larger ones. So that's on the theory side. On the empirical side, the objective again is to test these implications of the model, whether demand is more likely to go unfulfilled in less dense regions, and whether that is more pronounced for smaller platforms. The challenge obviously here is that unfulfilled demand is not observed. You don't see who would have taken a ride but did not end up with one. Even platforms themselves do not have the full data on this. So when region I has smaller demand, a smaller number of rides than region J, you can't really tell how much of it was because of lower demand and how much of it was because of lower access, quote unquote, to rights. And what we do to sort of get around this is we take note of a fact that we believe has been sort of overlooked in the literature, empirical literature, about passenger transportation markets. And that fact is, for every trip, there's a trip back by the same person. So to sort of illustrate the power of this, if riders use Lyft to exit region I consistently less often than they do to enter it, then we conclude that Lyft must have been undersupplied in region I, because the same people, the same population who chooses Lyft over other options to go to region I, on the average ends up systematically more likely to use other options, to choose other options over Lyft to exit. And especially if the same gap between inflows and outflows doesn't exist for other platforms such as Uber, then our conclusion that Lyft must have been undersupplied there is stronger. So we build regression analyses based on this identification idea, and we find out that indeed supply seems skewed away from demand towards denser areas in rideshare markets. And indeed, it seems that the skew is more pronounced for smaller platforms. So it's going to be in the paper, but not in the talk today, that the skew seems much more pronounced for taxi compared to rideshare. So that's on the empirical side. On the implication side, for business strategy, we argue the platform should incentivize drivers to operate in less dense areas through higher wages, but at the same time, the platform should avoid passing on all of that extra wage to passengers in the form of higher ride prices. I'm not going to have time today, but some platforms do a bit of this, not quite. Some platforms do not do much about this issue. On the policy side, what we argue is that breaking up or downsizing a rideshare platform which is something that is already being debated in some cities, is, of course, it's going to have some effects that are good for consumers, but there's this one unintended consequence, which is downsizing a platform is going to disproportionately hurt outer areas because it's going to further encourage a distribution of drivers that is overly clustered in busier areas. And our analysis shows that a minimum required size for a city like New York is about 120 rides per day to sort of prevent the sort of skew of supply away from the outer areas. I'm going to skip the related literature in the interest of time today, and I'm going to jump right into the model. There are I greater or equal to 2 regions. Each is a circle with size Ti. Price of a ride in region I is Pi. Driver wage is Ci. Each region I has a demand arrival rate of lambda I of Pi, which is given by potential demand lambda I bar times a fraction of rides F of Pi that, as a function of price, would request rides. Without loss of generality, we assume that the density of potential demand is going to be decreasing in the index of the region. Sorry, decreasing in the index of the region. Region 1 is the highest demand density area. Region I is the lowest demand density area. There's a total mass of capital N drivers playing a simultaneous game. Each driver chooses a region in this game, region I, in order to maximize her total revenue per hour. And the driver does it as a function of what the other drivers are doing. The total revenue is given by Ci, the wage of the driver in that area, divided by the total wait time in the area. The total wait time Wi of Ni, where Ni is the number of drivers present in the region, has 2 components. The first component is idle time, which is the time it takes for the driver to get assigned to a passenger request, and the pickup time, which is the time it takes the driver to arrive at the pickup location. The first component, the idle time, is increasing in the number of drivers and I in the region. It is not counterintuitive. The more drivers there are in the region, the longer you have to wait to be assigned to a request. The second component, pickup time, is decreasing in the number of drivers. The more drivers are there in the region, the less likely you are to be asked to do a pickup that is very much far away from you. Okay? And finally, we define this concept called access to rides in region I, which is given by the number of rides per hour in region I, normalized by the potential demand in that region, okay? And one can show it is always less than or equal to 1. The concept of equilibrium is simple. An allocation of drivers and 1 star through n capital I star is an equilibrium. If no drivers under that allocation has the incentive to change the region she's operating in and be able to strictly increase her total revenue per hour. I'm going to skip the discussion of selection, but it is in the paper. And I'm going to get into the results. We first look at driver behavior, fixing platform strategy at uniform prices P and wages C across all the regions. And we look at the distribution of drivers in the equilibrium. And the first result is that the distribution of drivers is skewed towards denser region. Formally, if the equilibrium allocation is n star, access to rides is higher in denser areas. Namely, if you look at regions I and J, where region I has a higher demand density compared to region J, then under equilibrium allocation, access to rides, which is supply normalized by demand, is higher in I than it is in J. This is exactly the idea that I said in the beginning. If region I has twice as much demand per square mile, in the equilibrium, it's going to get, say, 3 times as much supply per square mile. Okay? And now we are going to think about the effect of platform size, or in other terms, market thickness. Recall the primitives of the model are lambda bar, which is the vector of potential demands, n, the total number of driver, and t, the vector of platform, the vector of region sizes. We think of a 2-sided thickening of the market as scaling up both demand and supply by the same factor. And we think of a 1-sided thickening of the market as scaling up only supply. And our next proposition says that when you make the market thicker in either of these 2 ways, which, by the way, preserve all of the demand ratios across all the regions, we show that this action is going to shift the supply ratios towards being more balanced. Or in other terms, if you make the market thinner, either in a 2-sided way or in a 1-sided way, make the platform smaller, preserving all of the demand ratios, what you're going to see is that the supply ratios are going to become more and more imbalanced towards the busier areas. Okay? So now what we're going to do is we're going to take a step back and think about what the platform will want to do. Here's a proposition. The formal version is in the paper. Informally, The platform optimal allocation involves some skew of supply from demand, but not as much as it arises in the equilibrium. Again, if region I has twice as much demand per square mile as region J, gets 3 times as much supply, maybe the platform will want it to have 2.5 times as much supply, okay? The idea is that the platform also doesn't like its drivers to do long pickups, but at the same time, drivers, when they make decisions on where to drive, they leave externalities on each other, which they don't internalize, but the platform does. Therefore, the sort of optimal allocation of drivers from the perspective of the platform is going to be different from what the equilibrium will be. The optimal allocation from the perspective of the platform involves some skew of supply from demand, but not as much as we see in the equilibrium. So the next question here is going to be, does the platform optimally use prices and wages to reduce the sort of spatial skewness of supply, and how? So to analyze this, the first thing that we need to do is we need to endogenize N, right? Because when we want to make the wages a policy lever for the platform, we have to also make the number of drivers endogenous, so we do that. And we set the reservation hourly wage, hourly income for drivers to this value C bar, okay? So the first result that we have then says, look at the equilibrium allocation N star under optimal prices and optimal wages by the platform. If you look at that, first of all, we have that the platform is going to incentivize drivers to drive in less dense areas. Namely, the platform is going to offer higher wages to offer in those areas compared to in higher density areas. Remember, when index I is less than index J, without loss of generality, we assume that region I is a higher demand density area, okay? So the platform is going to incentivize to drive in less dense areas. Of course, it's going to also increase the prices, but the pass-through is going to be below 1. Namely, the platform is going to foot part of the bill for the incentive that the drivers are going to drive in these less dense areas. Nevertheless, at the end of the day, still there's going to be some imbalance between supply and demand in the equilibrium, even when the platform is behaving optimally. Namely, even when we have P star and C star instead of uniform P and C, even then we see that the axis to right is higher in regions with higher demand density. And again, as a reminder, the axis to right is supply after being normalized by potential demand. And also, if your sort of density of potential demand is below some threshold, you're not going to get any supply, okay? So the second proposition is about the impact of market thickness. Again, it turns out that even when the platform is behaving optimally, when you make the market thinner, preserving all of the demand ratios, the supply ratios in the equilibrium are going to get further skewed away from less busy areas and towards busier areas, okay? So this is sort of the theoretical part of the paper. We show that there is skew and it is more pronounced for smaller platforms, both when the platform is behaving optimally and when the prices and wages are fixed and uniform. Now we enter the empirical side of the analysis. We use data, ride-level information on rideshare platforms from the city of New York, from Uber, Lyft, and Via, and some analysis on taxis, which I'm skipping in today's talk, but is going to be in the paper. The objective is, again, to test these two implications, access being skewed towards busier areas, and the sort of skew being more pronounced for smaller platforms. The challenge, to remind you again, is that unfulfilled demand is unobserved. Those who do not make requests because they expect the price or the wait time to be high, we don't see them, we don't observe those. Therefore, if one area has much lower activity compared to another area, you can't easily tease apart how much of it is coming from demand, how much of it is coming from supply. Of course, the solution we're going to offer is not going to be a perfect solution, but we believe it gets you quite a bit of the way there. So what we say is we look at relative outflows. If the outflow of rides for a certain platform in a certain region is consistently much lower than inflows, we say that platform must have offered lower access to rides in that area, because it means that the same population who choose that certain platform to go into the area over other options, they systematically are more likely to choose other options over that platform to exit the area. And especially if this gap between the outflows and inflows is not present for other platforms, we are going to be able to infer that the platform is sort of undersupplied in that area. So in case I don't have time to show you regressions, let me just show you some figures which I believe will be informative. This is the graph of relative outflows, namely the number of outgoing rides divided by the number of incoming rides at the borough level, shown for different rideshare platforms in NYC in different years. As you see in all of them, the relative outflow, the number of outgoing rides divided by the number of incoming rides, is always the highest in Manhattan. And as you go towards the outer boroughs, it decreases. That's the first pattern that we observe. The second pattern that we observe is that this gap between the relative outflows of Manhattan and the outer areas is wider for smaller platforms. For example, for Lyft in Staten Island, for every 100 rides that go in, close to 60 rides go out, which means a lot of the people that choose Lyft to go to Staten Island end up having to choose other options to leave this borough. And the same gap between the relative outflows of Staten Island and Manhattan does not exist for Uber, which is bigger. And it does not exist as much for Lyft when it grows in size in 2018, but it is really big for Via, which is smaller than both of them, okay? So that's the first pattern. The second thing that I wanted to say is that you can sort of see the same thing even when you look at the zones level. If this is the heat map again of relative outflows, and you see that at the zone level, we have the same pattern. We test this with some regressions. We regress relative outflow on platform size, borough population density, and the interaction. And the interaction coefficient is what is important. If it's negative, it means that the larger the platform, the smaller the difference between the relative outflows of higher and lower density areas. And the coefficient is negative and significant exactly as the model predicted, no matter the specification. It's very robust. The second pattern that we observe is that relative outflow, which is number of pickups divided by the number of drop-offs, is highly correlated with the number of drop-offs divided by the size. So this is counterintuitive because drop-offs are in the numerator here and denominator here. But again, it's pretty much in line with what the model would predict. The number of rides normalized by potential demand is correlated with potential demand normalized by size. We test this using a regression again, and the coefficient comes back positive and significant no matter the specification. More details in the paper. Let me quickly summarize. The density is important and shapes the distribution of supply in spatial markets. In particular, in ride-sharing, drivers overcluster in busy areas. Platforms should optimally mitigate this overclustering, and the problem is more pronounced for smaller platforms. Future research could look at platform competition and how that could impact spatial distribution, especially as it relates to density. On the empirical side, one could look at quantifying the optimal spatial policy by platform. We theoretically characterize and we empirically suggest that this is relevant, but we do not empirically exactly quantify it, which we believe is an important, interesting avenue for future research. That's all. Thank you.